In this video, we'll be solving the integral of u over u squared minus 4u plus 13 quantity squared. The first thing I'm going to do is look at how the denominator is related to the numerator. For this, I'm going to ignore what's outside the parentheses. So I'm only looking at the u squared minus 4u plus 13, and I'm comparing that to u. In a perfect situation, if I take the derivative of u squared minus 4u plus 13, I would get 2u minus 4, which would be the same as the numerator. But I don't have that in this case. So my goal here is, can I make u into 2u minus 4? So we're going to actually do that. If I have 2u minus 4, I need to subtract u and add 4. Because now 2u minus u is just u, and the negative 4 plus 4 cancels out. So those two are equivalent, those two integrals. Okay, now at this step, I'm going to break this integral into two. The first one, I'm going to have a 1/2 outside. I'm going to have 2u minus 4, the numerator. And the second integral, I'm going to have 2. So these are all equivalent so far, all these steps. Because the first integral, the 2u minus 4, when I multiply that by 1/2, I end up with u minus 2. And when I add it to the other integral's numerator, the 2, that becomes just u. So that works out nicely. And now I can let my w be u squared minus 4u plus 13, and dw is just 2u minus 4 du. So I can replace this whole integral with 1/2 integral dw over w squared. And on the right, I want to complete the square. But I'm going to take this step one step at a time. Okay, so I'm going to add the b over 2 quantity squared, where b is negative 4. So when I do that, I add a 4, and then I have to subtract a 4. That's to not change the value of the denominator. If I find the antiderivative of 1 over w squared, I get negative w to the negative first power, and I'm going to multiply that by 1/2. And in the second integral, I'm going to group the u squared minus 4u plus 4 together, and then the negative 4 plus 13 will become 9. In the previous slide, we had let w be u squared minus 4u plus 13, so I'm going to substitute that back in. And next, I can factor out the u squared minus 4u plus 4 as just u minus 2 quantity squared. The second integral now is what we're really after. I don't personally like the u minus 2. It makes things look more complicated than they are. So I'm going to make a substitution and let w equal u minus 2. So dw will be du. And now I can replace the integral as 2 over w squared plus 9 quantity squared times dw. And at this point, I'm going to have to use trig substitution. So I'm going to let w be 3 tangent theta. dw will be 3 secant squared theta d theta. Okay, I'm going to replace that and put everything in there. Okay, so my integral now is in terms of thetas. We're going to work with the 3 tangent theta squared first. And that's just going to be 9 tangent squared theta. Notice all that in the parentheses is still squared. So the 9 tangent squared theta plus 9 is currently squared. So the both terms have a factor of 9. So I can pull that out, and that'll become 81. Okay, because 9 squared is 81. And I can make some more simplifications. Okay, because tangent squared plus 1 is secant squared. And 3 over 81 is 1 over 27. Okay, now I have secant squared in the numerator, secant squared in the denominator. The secant squareds are going to cancel, and I'm going to be left with a secant squared in the denominator. Which now, 1 over secant squared is the same thing as cosine squared. So in order to integrate cosine squared, we can use a trig identity to write it as 1 plus cosine 2 theta over 2. And notice that the 2 in the 2 over 27 and the 2 in the denominator will cancel out. So I'll have 1 over 27 times the integral of 1 plus cosine 2 theta d theta. And I can easily integrate this as 1 over 27 times the quantity theta plus sine 2 theta over 2. And I'm going to add a constant c. Eventually I want to make a substitution back to what I used. But how am I going to do that with sine 2 theta? So the trick here is I'm going to use another trig identity, and I'm going to rewrite sine 2 theta as 2 sine theta times cosine theta. Notice that the 2's will end up canceling each other. So I'll be left with 1 over 27 times theta plus sine theta times cosine theta. And I'm going to let w be 3 tangent theta, right? Because that's what actually we had a couple slides ago. That was the substitution we made. So our goal is to go from theta to w back to u. So it's going to take us a couple steps to do that. So in order to make this substitution back, we need to draw a right triangle. The angle will be theta. And because w is equal to 3 tangent theta will be w over 3. So that's opposite over adjacent. Opposite side is w, adjacent side is 3. And doing the Pythagorean theorem, we get the square root of w squared plus 9 as our hypotenuse. Now we go back to our equation, and theta, well, the way we get theta is to get tangent by itself first and apply the inverse tangent. So theta will be the inverse tangent of w over 3. Now sine theta is opposite over hypotenuse, so that'll be the w over square root w squared plus 9. Cosine is adjacent over hypotenuse, and that's 3 over square root of w squared plus 9. And now that term is all in terms of w. So what's left is to rewrite this in terms of u's. Okay. We had, well, first I'm going to multiply the denominator, so the square root of w squared plus 9 times the square root of w squared plus 9 will just turn into w squared plus 9. And then we're going to go back into the substitution. We had let w be u minus 2. So we're going to replace every w with u minus 2. And that is my final answer.